Hi everyone. Till now we were discussing about samples that are linearly separable. We discussed the OR gate, the AND gate, and also we discussed about how the perceptron's convergence theorem works. We may have datasets which are not always linearly separable. However, we can use piecewise linear functions to separate out the classes. Effectively, we can get the region of interest in form of a convex polygon. We will now show a small numerical example demonstrating how to build a neural network from a bounded region of interest where the region of interest is bounded by linearly separable planes, as you can see in this image. Before proceeding further, let's try to understand what a convex region is in layman terms. Let's consider this region of interest, and over here I consider 2 points A and B, and I join them with the help of a straight line. Now, a region is going to be called a convex region only when a line joining any 2 points inside the region lies inside the region. So, if I take any two random point and try to join them with the help of a line, the line joining both the points should lie inside the region. Now, we may have a non-convex polygon as well. Like, let's say I draw a region like this. Now, if I consider a point over here, a point over here, let's say this is a point A, this is a point B, and I make an attempt to join them. Now, you can clearly see that the part of the line segment which is joining both point A and B is lying outside the region. So, if the star is effectively the region of interest, a part of the line, this part, or I can say this part, it lies outside the region. So in such a scenario, we can say that the region of interest is non-convex in nature. The polygon here in our example that separates out the positive and negative classes together is convex in nature. And in polygons like these, we will be having a neural network created that will give the convergence in finite number of steps. Or in other words, the perceptrons used to create a network will converge in finite number of steps as per the perceptron convergence theorem mentioned in part 2 of the video playlist. So as we can see, there are 4 points over here. We can find the equation of each of the lines AB, BC, CD, and AD. Let's refresh our high school mathematics a bit. Let's consider 2 points M, x1, comma y1, and another point is N, x2, comma y2. And if M and N lie on a straight line, this is M and N, both of them lie on a straight line, then the equation of line joining M and N is given by y minus y2 divided by x minus x2 is equal to y1 minus y2 divided by x1 minus x2. Now, considering this result in mind, we will proceed with finding the equation of line for AD. This is the equation of the line, or this is the, so we already found out that these are the 4 lines which make up the polygon ABCD. We will proceed with finding the equation of the line AD. We can clearly see that we have 2 points A and D. A is given by the coordinates 2, 5 over here, and D is given by the coordinates 5, 6, 5, 7. Now, if I have to find the equation of AD, I will just use the equation which we refreshed over here, with the only fact that this x1 and x2 are being used in the place of x and y, but the idea remains the same. And then we make an attempt to find the equation of AD, which is given as x2 minus 5, x1 minus 2 equal to 7 minus 5 divided by 5 minus 2. We solve it further, and then this is the equation we are getting for AD. Likewise, we proceed further and make an attempt to find the equation of DC. So this is how we are obtaining the equation of DC using the exact same formula which we refreshed previously. I will urge you to pause the video and check the calculations before proceeding further. In the same way, we are getting the equation of CB and AB. We use the same formula for calculating the equation of line. I hope if you are solving along, you are getting the same result as mine. So we started with 4 points and we have the equation of 4 lines as needed. So before we proceed further to tabulate and obtain a multi-layer perceptron out of the tabulated result, let's observe few things and set up a decision boundary, a function for decision boundary accordingly. Now, over here I have written the equation of 4 lines which we have derived till now. Now, if we watch carefully, all these equations are in the form of w1 x1 plus w2 x2 plus b equal to 0. So corresponding to each of these lines, we can find the values of w1, w2 and b. Just to give an example, if I consider the line CB, over here the value of w1 is equal to 1, value of w2 is equal to -3, and the value of b is equal to 6. We will establish the decision rule now, which states that the output will be equal to +1 and -1, and +1 will happen only if the value of w1 x1 plus w2 x2 plus b is greater than or equal to 0, and -1 else. And else is happening when the value of w1 x1 plus w2 x2 plus b is strictly less than 0. Now let's try to understand what this decision rule actually means. What we are saying over here is the fact that any point to the right of the equation of line w1 x1 plus w2 x2 plus b equal to 0, which could be any line, something like this. Let's say anything towards here is going to be positive and anything to the left is going to be negative. And this is applicable for all the lines which we have in this polygon, like let it be AD, DC, CB and BA. So for all the lines, we set up a decision rule which says that anything to the right is positive, anything to the left is negative. Since we have now established a decision rule, we know that the equation of line is in the form of w1 x1, w2 x2 plus b. Let's go through each of the equation of line and try to see how the decision rule works. Let's try to see first the equation of line AD. This is the equation of line. I can see that the value of w1 is 2 and the value of w2 is -3 and the value of b is 11. Remember, we are using the equation in the form of w1 x1 plus w2 x2 plus b. Now, to see how the decision rule works, let's go to the image which we have already and take a point which lies inside the image. And for the sake of convenience, I will take a point 3, 4. So over here x1 is equal to 3 and the value of 4 is taken by x2. Now this was 3, 3, the point B. Now if I go a bit up over here, we probably will get a point E which is 3, 4, and this lies entirely inside the equation of polygon. Now let's try to understand that if I have a decision rule like this, 2x1 plus 3x2 plus 11 greater than equal to 0, then only it will be 1. Let's try to plug in 3, 4 over here in the place of x and 1. I will be getting somewhat like 2 into 3 minus 3 into 4 plus 11, and on solving we get the value as 5. Now the value of 5 is greater than or equal to 0, which will mean that if I follow the decision rule over here, the outcome in the region shaded, which is actually the region in pink, you can see it's all consisting of positive region, is going to be +1. So if I rely on the classification made by AD, anything which is going to fall in this region is going to be classified as positive. However, anything which is falling outside the region, like if I consider a region over here, or a region over here or even a region over here, it's also going to be classified as positive. We don't need that misclassification to happen. Now we will proceed further to find the equation of DC. Like we have the equation of DC, we have the value of W1, W2, B, and this is the decision rule which we established. And if you are thinking why this decision rule is happening, this is because we defined our decision rule in such a way that if the equation of line is greater than 0, that's positive, else negative, or anything to the right of the line is positive, anything to the left of the line is negative. Now I will allow you to think intuitively, like I have the equation of line DC. If anything is to the right of DC, as per our decision rule, it's going to be positive, and anything to the left is going to be negative. Now, whatever is going to fall inside this region is going to be negative. Now, we will validate it with the 0.34 which we have considered over here, and then we will calculate 3 times 3 plus 4 minus 22. And this is a term which is very less than 0. It's minus 9, which is less than 0. So over here, the outcome is going to be negative. So we followed the decision rule, outcome is negative. Similarly, we go to the line CB. We have the equation of line over here. The value of W1 is 1, W2 is minus 3, B is 6. And this is our decision rule, which we have set up, which is like W1 x1 plus W2 x2 plus B is greater than equal to 0, then only we are going to have plus 1 or minus 1. Now this value is coming out to be 3 minus 3 into 4 plus 6, which is minus 3, which is again less than 0. Now, if you look carefully, actually the value is going to be minus 1 here as well. Now, if you look carefully in the diagram, the value of CB is presented over here. Now, anything to the right is positive, anything to the left is negative. Now, anything to the right is positive will mean that all these regions which are green in nature over here, these are going to be positive for CB, whereas the entire pink region, which is actually consisting of positive samples, are going to be negative. So any point in the region, this line is going to misclassify it completely, right? So we proceed further for the last line we have, last equation of line we have, which is AB. Now the equation of line AB is given as this. Value of W1, W2 and B is attained. We establish the decision rule we set up, and intuitively it looks to be a positive value only. Now if I actually plug in the value 2 into 3 plus 4 minus 9, which is equal to 1, which is greater than 0, this will mean that the outcome in the decision boundary is positive, and this validates as well. If I go to AB over here, this AB will, just a minute, this AB will say that anything to the right is positive, so it's actually classifying correctly in the decision boundary at least, and anything to the left is going to be negative. So this is the outcome which we are getting by following all the equations. Now if we think carefully, if I just analyze this first column and the last column, we will get a correct prediction only if we listen to AD, which is this. If we listen to this, and AB we listen to this, and do exactly opposite of what DC and CB are telling. So this table tells us how to correctly identify a point inside a polygon. If a point lies inside a polygon, it will be positive, else it will be negative. Once this table is established, it won't take much time to translate this table to a neural network which eventually looks like this. So let's try to understand what this neural network actually means. So this layer entirely is the input layer. It will take into account the value of x1 and x2. Let's try to understand first this node for AD, and then all the other understanding will be a bit easy for you to follow. So once we get the input node, we take the equation of the line AD and corresponding weights W1 and W2. Those are going to come over here. This is W1, which is equal to 2, and this is W2, which was equal to minus 3, and whatever was the bias term, which was 11 over here, this is going to come inside the hidden layer. Now, whatever decision is taken, this is the decision taken, or you can say the outcome in the positive region, it's going to come over here. Likewise, if I consider the node DC, the x1 and x2 are going to be as they are in the input layer. The W1 is represented here, the W2 is represented here, 3 and 1 respectively. The bias term is represented inside the node of the hidden layer, and the decision which we are taking, the value of minus 1 is represented over here. This is minus 1. Likewise, for CB, we move ahead. This is the value of W1, which is 1, because it's coming from X1, and likewise this is the value of minus 3, which is coming from X2. The bias is written inside the node, which is 6, and this is outputting a value of minus 1, which is taken from the last column over here. We write it over here. Likewise, if I consider AB, which is the last node which we have, last node of the only one hidden layer which we were able to draw. The value of W1 and W2 are 2 and 1, which are correctly pointed out over here. And the value of bias is minus 9, and the output value of plus 1 is mentioned over here. Now, if we look carefully, we have to follow the same decision rule while being in the last node as well. This is the output node for us. So we were able to get till the output node, and we need to find out how exactly I am getting the value of 4 over here. So as we discussed previously, the correct predictions are done by the model if we listen to AD and AB and do exactly opposite of what DC and CB says. Now, if we do that, if I listen correctly to AD, then we have the outcome of the decision as plus 1. We multiply it with plus 1, and if I have to negate what DC has to say, then I have to multiply it with minus 1, and if I have to exactly negate what CB has to say, I have to multiply it with minus 1 again, and if I have to agree to what AB says, I multiply it with plus 1. So on solving this entirely, I get the value as 4. To validate whether this network is actually able to perform the classification task properly, we will consider a point within the network and also a point outside the network. And we will put the points in the network and then try to see whether the model is able to give correct results or not. So we consider a point 4, 5 over here. So let's not look into the diagram and first try to find out what the neural network says and then validate it with the diagram. And let's try to see what we get at this node 1. So the node 1 is twice of W1 minus 3 times W2, or twice of 4 minus 3 times 5 plus 11. So the value of this is going to be 4. So 4 is very much greater than 0. So that's how you are getting the value of Z1, or the outcome which is coming at this node as 1. Likewise, if I consider the node number 2, this is 3 times 4 plus 1 times 5 minus 22. So this is minus 5, 12 plus 5, 17, yeah. And this is clearly less than 0. And that's how we are getting the value of Z2 as minus 1. Likewise, for node 3, we have W1 and W2 as 1 and minus 3. We take 1 into 4 minus 3 into 5, and the value of bias is 6. So if I calculate it, I get minus 5 again, which is again less than 0. Hence the value of Z3 is minus 1. And the outcome at node 4 is going to be twice of 4 plus 5 times 1 minus 9. So 8 plus 5, 13, minus 9 is 4, which is positive. So the outcome at node 4 is going to be positive. Now we try to find out the outcome which is going to the output layer. So this is the output node. So we say that this is the decision rule at the output node. It's exactly the same decision rule which we have established previously, just that we are modifying it at the output step. So the decision rule we established was for the hidden layers, these, and these. And this is the decision rule for the output layer, which is exactly the same decision rule which we have established for the hidden layers. Now, this is the decision rule, and we have the value of W11, W12, W13, and W14 calculated as well from our previous discussion. And the value of ZIs have been calculated just over here. So on multiplying this, we are getting the value as 4. Now, since 4 is obtained, and if I follow the decision rule, we are going to get the final decision as 1, because we have the equation of W1 Z1, W2 Z2, and so on. Now, if I subtract it with 4, which is actually needed over here, I am going to get the value as 0. And since 0 is greater than or equal to 0, we get the final decision rule as +1. So according to the model, this is going to be a positive point. Now let's check visually where exactly the point 45 lies. Let's go back to the image, a better one. Yeah. So over here, I can see the point 4 on x-axis is going to be somewhere here, and the point 5 is going to be somewhere here. I plot the point, it is going to be somewhere in this line, which is very much in the positive zone, and hence what we can say that the model prediction are correct in this scenario, or we were able to model the region which is convex in nature, as we have discussed previously, with this model. Now let's consider a point which lies outside the region and validate whether the model is correctly able to identify it as a negative point or not. For that, I considered a point 1, 1. I use the same argument as I did before, or in fact, let me paste the value of neural network or the diagram of neural network over here. On looking carefully, if I observe the equation of first line, I am getting twice of 1 minus 3 times 1 plus 11, which is equal to, I think, 11, 10, which is greater than or equal to 0. Hence, the decision is going to be +1. Likewise, if I go to node number 2, I am getting minus 3 times 1 plus 1 times 1 minus 22, which is clearly a term less than 0, hence minus 1 is there. And let's follow what we get at node number 3. It's 1 into 1 minus 3 into 1 plus 6, which is a term greater than 0, hence we are getting a value of 1. And eventually at node number 4, I am getting twice of 1 plus 1 into 1 minus 9, which is less than 0, and I am getting a term as minus 1. Now let's try to solve it. What we are getting over here, the equation of decision boundary, W11 Z1, W12 Z2, W13 Z3 plus W14 Z4 minus 4. So I have obtained all the ZIs over here. The value of W11, W12, W13 and W14 is present over here. On solving them completely, what we can see over here is the fact that we are getting the value as minus 4, which is clearly less than 0, as pointed out over here. And as per our model, the final result is minus 1, which means that this is a negative point, 1, 1. Now let's go back again to the image which we have of the region and see where 1, 1 lies. Let's say this is the image which I selected. 1, 1 lies somewhere over here, which is clearly a very negative point, and hence our model was able to correctly identify in this scenario as well. So to summarize, we were able to determine a neural network entirely from a set of points from a convex decision boundary. Now we need to answer the question of what happens when the decision boundary is non-convex in nature. In the next video, we will be considering an example where the decision boundary is the union of two convex decision boundaries, and we will make an attempt to determine a neural network in such scenario. Thanks for your time.